Hey guys, welcome to the OneClass channel. My name is Sydney and I'm currently a third year engineering student, and today we'll be going over some commonly asked math questions at both the high school and university level. If you need any additional homework help or tutoring, you can check out the links in the description below and we can get started. Okay, the first question asks us, what is the volume of a hemisphere? So first of all, what is a hemisphere? So a hemisphere is basically a 3D object that's half of a sphere. Okay, so you can kind of imagine it. So if we have a full sphere, remember it's a 3D object, and we slice it in half like this. Oops. If we slice it in half, sort of just like slicing a ball or an orange or something like that in half, this top half, or I guess either half, would be two different hemispheres, okay? So what we're doing is looking for the volume of the shaded in area. So on the left here, we have a little diagram of what the hemisphere looks like, right? So this hemisphere will have a radius of r, which would be the same radius as the sphere does. The sphere has. So r is the radius. Okay, and that will be given. So we know already that the volume of a sphere is equal to 4 divided by 3, 4 over 3 times pi r cubed. And since we know that a hemisphere is half of a sphere, then we can say that the volume of the hemisphere is equal to the volume of a sphere divided by 2. Okay, so remember I shaded in the top half here, and that is representing half of the total volume of the sphere. Okay, so as we said, we know what the volume of the sphere is, so all we have to do is sub that in. So we have 4 divided by 3, 4 over 3, pi r cubed divided by 2. So from here, we can think of it also as 4 over 3 pi r cubed times 1/2. And we can cancel out the 4 and the 2. So basically 4 divided by 2 here, and you get 2 in the numerator. So you're left with 2 over 3 pi r cubed. Okay, and that would be the volume for a hemisphere. For a hemisphere. Okay, so hopefully I didn't block anything here. Let's look through the solution. So we have our drawing of the hemisphere, just the half of the sphere, and this also goes through an example, so let's do that. So our example shows that we have a radius that is equal to 2 centimeters. Okay, so like I said, you would have the radius of the sphere or hemisphere already given to you. And then we just need to plug that into the equation that we derived. So we have 2 over 3 times pi r cubed. So subbing in 2 centimeters for r cubed for the radius, we have 2 centimeters cubed. And from that we will get, well, you can do an exact solution if you'd like without evaluating the pi. So that would look like 2 cubed times 2 divided by 3, right? So I can just write this like as I said so that there's no confusion. By 3 or times pi centimeters cubed. If you evaluate just that first part, you get 5.33 centimeters, or pi, sorry, times pi centimeters cubed. That would be the exact solution, and then the evaluated solution using your pi would be, as you can see here on the left, 16.7467, oops, 7 centimeters cubed. Okay, so that would be the volume of your hemisphere when a radius, the given radius is 2 centimeters. And once again, we have the solved volume of a hemisphere that we got from the volume of a regular sphere. Okay, so correct solution. And that's good. Move on to the next question. Okay, question number 2. If we're asked, okay, so how do you find a polar equation of the form r equals to a function of theta for the curve represented by the Cartesian equation x equals to 3? Okay, so first of all, we are given the Cartesian equation, which is x is equal to 3. And what we want is to convert this from Cartesian to polar equation. Sorry, it keeps drawing those lines. Equation of the form r is equal to a function of theta. Okay, so that essentially means that, well, our solved solution will have r on the left-hand side, and then we'll have a function including theta usually. Okay, so what we can do is look at our conversion factors. So usually when you're converting from Cartesian to polar, we have that here. All right, these are our conversion factors, or conversion from Cartesian to polar. We are given that x is equal to r cosine theta, and we are also given that y is equal to r sine theta. Okay, so with this, we can easily convert our given equation. So remember, we were given x is equal to 3. I used blue, but that's okay. So if we have x is equal to 3, we can substitute our x is equal to r cos theta right into the equation. So we have r cos theta is equal to 3. And remember, for our polar equation, we want it to have r is equal to a function of theta, so r is on the left-hand side. So isolating for r, we divide both sides by our cos theta, and these cancel out, so we get r is equal to 3 over cosine theta. And that is the converted polar equation from x is equal to 3. Let's look at the solution. So given our x is equal to 3, we can use a relationship between polar and Cartesian equations, where it gives you what x is equal from Cartesian to polar, and what y is equal from Cartesian to polar, and then just substitute in what x is equal to in polar form, and we can solve for r to get r is equal to 3 over cosine theta. So correct solution. All right, and that's all for that question. Okay, question 3 now. We are asked what is the square root of 36, okay? So you might already know this off the top of your head, but if we apply some tricks, we can learn how to solve this type of question for different values instead of 36, for example. So what we're going to do first is express 36 as a product of its prime factors. Of its prime factors. So thinking about prime factor, we can think of a factor tree, which that might help you split it into its prime factors. So this is called a factor tree. So if we want to split 36 into prime factors, you can think about dividing it by a prime factor. So thinking about dividing this by 2, right? What's 36 divided by 2? Well, that's 18. And then we can continue to divide this by 2. And so 18 divided by 2 is 2 and 9. And then, 9 can be only divided by 3 twice. So, or 3. And then 9 divided by 3 is 3. Okay? So from this factor tree, we are able to find that 36 has these 4 prime factors. We have 2 times 2 times 3 times 3, okay? And multiplying those prime factors, you'll be able to get 36. So if our original goal was to express it as a product of its prime factors, let's write it like that. So we have 36 is equal to 2 times 2 times 3 times 3. So now that it's in its prime factors, what we can do is we can group pairs of prime factors, okay? And they have to be the same number. So we have the 2 times 2 as one pair, and we have the 3 times 3 as another pair, okay? And the reason for doing that is because now you can see that 2 times 2, well, that's just 2 squared, right? Because a square means multiplying it by itself, and then multiply that by 3 times 3, which is 3 squared. And now that you have 2 squared values underneath the brackets, well, since everything is multiplied, you can, or not brackets, sorry, underneath the square root, you can imagine, separating it into 2 different values being square rooted as well, since they are being multiplied. So now we have a square root under a square, or a square exponent under a square root, which ultimately cancels out, so we get 2, and then the square root and the squared exponent cancel out, and we get 3. And then you can find out that the square root of 36 is equal to 2 times 3, which is 6, right? And we know that from our multiplication tables, right? 6 times 6 is 36, so that's the opposite operation. So an alternative way that you can do this is going from our, if you don't know the rule that the square and the square root will cancel out, if you represent this same thing in exponent form, maybe it'll be a little bit more clear. So square root is equivalent to writing a half as an exponent, right? So we have 3 squared, 1/2 as the outer exponent. And when you have a bracket with an exponent on the outside of the bracket, you multiply the exponents, okay? Oops. So to apply the exponent into the bracket, you multiply 2 times 1/2 for the entire exponent. We have 2 times 1/2. And we know that 2 times 1/2 is like 2 over 2, which is 1. So you get 2 to the 1 and 3 to the 1, which, as you can see, leads you back to 6. So just another way of thinking about it, if the first method wasn't clear. But you'll get the same answer of 6 for the square root of 36. Okay? So in our solution, we're first expressing 36 as a product of its prime factors, grouping the pairs of the same factor, and I skipped a couple of the steps that I wrote, but we get the same thing of 6 for the answer. So I'm select part of the solution. And that's all for that. All right, question 4. Question 4. So we're asked to prove this trig identity, okay? So we have secant x plus cosecant x divided by 1 plus tan x equals to cosecant x, okay? So let's first think of some trig identities that will be able to help us, okay? So trig identities. So these can be helpful. We have cosecant x is secant x is equal to 1 over cosine x. We also know that the cosecant x function is equal to 1 over sine of x. And we also know that tangent or tan of x is equal to sine of x divided by cosine of x, so you want to say it. Okay, so that covers the secant, cosecant, and the tan, and that's cosecant again. So that's everything we will need. Hopefully I don't block it. Okay. So we can start to solve our identity. So let's sub everything in. So for secant, the first term, we can already sub in our identity of 1 over cosine x plus cosecant x, this term, which we said for our identities is equal to 1 over sine of x, and then all over our 1 plus tan of x up here, which we said our identity is sine of x over cosine of x. And that is all equal to cosecant x, which once again we said is 1 over sine of x. All right, let's move this up a little bit. Okay, so now that we have this, we can work with our fractions. So this error might be a little confusing. Okay, so working in the numerator first, if we have 2 different denominators, we are going to find a common denominator. So I'm going to multiply our left-hand fraction here with sine of x over sine of x, which is effectively 1. That's why we're allowed to multiply it, right? Cos x. So this is what it was originally. And now the right-hand side, the right-hand fraction here, we will multiply that by cos. I'm going to run out of room, so let's zoom out a tiny bit. That's cos of x over cos of x. Multiplying that by this term, which is essentially 1, right? The whole term, within the bracket. And that is just to get the common denominator, because now across the denominator for both of the fractions, we have sine x cos x, right? So we'll do that in the next step, but first let's look at the denominator here. The denominator of the entire fraction. We have cos x in the denominator of this fraction, so I'm going to multiply our 1 here by cos x times cos x. Cosine x, not really a bracket, cosine of x there, times the 1 that we already had, plus the same fraction that we had before, okay? Which is sine of x over cos of x. So this one stays the same. And then on the other side, we will just leave it as is on the right-hand side of the equation. Okay? So let's go back to this numerator here. So now we have common denominators, which means we can add our fractions, okay? So like I said, we have sine of x and cos of x in times cos of x in both of the denominators for these fractions. So for this fraction in the numerator, we have sine of x on this side plus cos of x on this side. And remember, in the denominator, we have our common denominator of sine x times cos x. All right? Hopefully these aren't confusing you. And then in the denominator, I don't know if I got that mixed up. I didn't mean to say it like that, but okay, we have cos of x in the denominators of both of these now, so that means we can add them. So we get cos of x, cosine of x, plus sine of x, all divided by our common denominator of cosine of x, and that is equal to 1 over sine of x on the right-hand side. Again, that doesn't change. So we have two fractions being divided, okay, which is a lot of fractions. So what we're going to do is change the way this is written. So we have our fraction that's in the numerator here. That's sine of x plus cosine x divided by sine x times cos x divided by cos of x plus sine x divided by cos x. So I'm not changing anything, I'm just changing the notation for how it's divided so we can see clearly what we're doing. That stays the same, the right-hand side stays the same. And so when we have a fraction that is being divided, we can change this to multiplication by taking the reciprocal. So the reciprocal of this fraction means the fraction when it is flipped. So the numerator goes to the denominator and the denominator goes to the numerator. We'll see in a second. So the first fraction we have stays the same, cos of x divided by sine x cos x. And the one that is being divided currently, this one here, we are now going to multiply after we flipped it. So this is the reciprocal when it is flipped. We have cosine of x in the numerator now, and cos of x plus sine x in the denominator now. That is equal to the same thing. This side doesn't change. Okay? So now you can see we have two terms that are the same. We have our sine of x plus cos x, and cos x plus sine x. Obviously, when you're adding, the order doesn't matter, so we can cancel those two out because they are the same, and they're being multiplied. So basically, you can imagine this as one giant fraction, and so we have sine of x plus cos x divided by cos of x plus sine x. So they cancel out. And then you can also see that we have 1 cos x here on the bottom and 1 cosine of x on the top. So we can cross those out as well. And hopefully with all these lines, you can still see that we have a sine of x in the denominator. So we have left over 1 divided by sine of x. And surprise, surprise, on the other side the equation, we also have 1 over sine of x, which we haven't changed this whole time. So we can see that the left side is equal to the right side. So sometimes people write it like this, left side equals right side, and therefore QED, like basically we are asked to prove it and we were able to prove it. So that is the solution for that question. Let's look through. So we're given the following identities. I think typically you would need to memorize these for class, but if they're given, even better. We have them here, and we start by converting everything into their trig identities of just sine and cosine, and then we can cancel out fractions. They canceled out while still in fraction form, which you can also do, so you can skip this reciprocal business if it makes sense to you already, and you will end up with the same proof. So we have the correct solution. Oops, and we can move on to the next question. All right, so question 5. This question is asking us what is a composite number between 10, or what are the composite numbers, between 1 and 10. So what we want to be able to explain, first of all, is what is a composite number? Composite number. So essentially, a composite number is the opposite of a prime number. Opposite as a informal term for opposite, just a way to understand it, not necessarily mathematical opposite or anything like that. But basically what a composite number is a number that can only, or that can be, not only, that can be divided by more numbers than just 1 and itself. Oops. Itself, but I should say without leaving a remainder. Okay, so the reason why before I said that it's opposite of a prime number is because prime number can't be divided by anything other than 1 and itself without a remainder, okay? Meaning it won't divide and leave an integer. But a composite number can be divided by more than just 1 and itself and still remain an integer. So let's look at our examples of numbers 1 through 10. So let's start with 1. 1 we know is a prime number, so it's not a composite. And that is because it's a prime number, which means it can only be divided by 1, and I guess it can only be divided by 1 and itself, but that's redundant since it is 1. So yeah, it can only be divided by 1. If you were to divide it by anything else, you would get not a whole number or a fraction or a decimal. not an integer. So that makes it not a composite number. Let's look at 2. Well, 2 we know is also not a composite number. We can only be divided by 1 and itself. Okay, so 2 divided by 2, or you could do 2 divided by 1. Those are the only ways that you can divide it while having a answer that is a whole number. Okay, so we continue. We have 3. Well, we can only divide that by 1 and itself again, so that makes it not a composite number. And I won't write the explanation again since we already saw it, but it's once again not a composite because it's a prime number, as was 2 and 1. Let's look at 4. Now 4 can be divided by other numbers, so it can be divided by, well, not just 1, but also 2 and 4. 2 is the one other than 1 and itself. 4 is itself. 1 is 1, obviously. So because it can be divided by a number other than 1 and itself, therefore it is a composite number. A composite number. Right. Next is 5. This we know is a prime number, so it is not a composite. Composite is not a composite number. It can only be divided by 1 and itself. 6. Well, 6 can be divided by 1, 2, 3, and 6. 3 and 6 being other than what would make it a prime factor, circling the composite numbers. So this one is also a composite number. Be divided by more than just 1 in itself. We have 7 next. 7 we know is also a prime factor, prime number, so it's not a composite. Sorry, 1 second. It is not a composite because it can only be divided by 1 in itself. We have 8. This can be divided by, I'm just going to say divided by 1, 2, 4, and itself. So therefore, it is a composite number since it can be divided by 2 and 4 as well as 1 and itself. And then we have 9. Well, that we know is divisible by 1, 3, and itself. So since it can be divided by 3, it is also a composite number. And finally we have 10. 10 can be divided by 1, 2, 5, and 10, which is itself. Since it can be divided by 2 and 5, that's, oops, running away. There we go. So that's also a composite number. Composite. All right, so in the end, let's look at what we got. Circled here we have 4, 6, 8, 9, and 10. So you can say 4, 6, 8, 9 and 10 are composite numbers, between our 1 and 10. Okay? Looking at the solution, composite numbers are numbers that can be divided by other numbers without any remainder, except for 1 and itself. So other than 1 and itself. Otherwise, those numbers are called prime numbers. Those are numbers that which can only be divided by 1 and themselves. And we are looking at numbers between 1 and 10. We found that we got 4, 6, 8, 9. I guess they didn't include 10 because it was not within the range technically, but we have the correct solution. Okay. Question 6. So we are asked another trig identity question. So we are given cos of x divided by secant of x minus tan of x is equal to 1 plus sine of x. And we're asked to prove that each side is equal. Left side is equal to the right side. So first we can write down some trig identities that might be helpful to us. So let's see, trig identities. Here we go, oops. Trig identities. So we see that we have secant x, that is equal to 1 over cosine x. And we also have tan of x, which we know is equal to sine of x divided by cosine of x. Okay, so with our trig identities, we are able to solve. Let's start by subbing them in to our given question. So we have cos of x in the numerator on the top. And in the denominator, we can sub in 1 over cosine of x for secant x minus tan of x, which we'll sub in as sine of x divided by cosine of x, the identity for tan of x. And that's equal to the right side of the equation, which we will keep the same. Sorry about these lines. Okay. Now what we can do, let's work with this denominator here and figure out the fraction. So cosine of x stays the same in the numerator. And so we can see that these two fractions in the denominator have the same denominator already, which is cosine of x, which means we can readily add them. Or in this case, subtract them. So we have 1 minus sine of x divided by cosine x is equal to the same thing on the right-hand side still. Okay, and you might be able to see that we have cos of x in the numerator and cos of x in the denominator of the denominator. But in case you don't see it, let's go through each step. So let's rewrite this fraction. Instead of writing it in a fraction form, we'll write it with the division sign. So we have the same thing that we've seen here in the denominator, just as the divisor. So 1 minus sine x divided by cos x is equal to 1 plus sine x on the right-hand side, which is the same. And when you have a fraction that is being divided like this, we can change it into being multiplied. So instead you will have it multiplied by the reciprocal. And the reciprocal of a fraction is flipping the numerator and the denominator. So that means we will get cosine of x instead now in the numerator, and we'll get 1 minus sine of x in the denominator. So we have 1 plus sine of x still on the right-hand side. All right. Now with this, you can see we have cos of x times cos of x, which is equivalent to cos squared x. And the numerator, 1 minus sine of x, is equal to 1 plus sine of x. Okay, so now we're going to use a new identity because now we have a cos squared x. Okay, so let's write down this identity. This is the Pythagorean, what are you spelling it wrong? Pythagorean identity, or trig identity, I guess let's say. Trig identity. And that is that cos squared of x plus sine squared x. I kind of am writing the brackets and not writing the brackets, but you understand that it means the same thing. And that is equal to 1 when you add them. So you can see here in the numerator, we just have cosine x squared. So let's rearrange for that. We have cos of x squared, or cos squared of x, is equal to 1 minus sine squared of x, just by subtracting it from both sides and moving it over. So let's sub this in for our cos of x, which I had circled up here. Otherwise, we're going to draw the whole line. There we go. So let's sub that in here, and we get 1 minus sine squared x over 1 minus sine x is equal to 1 plus sine x. So we're super close now. We can actually expand this term on the numerator. If you think about it, like instead of sine of x, you have a. So let's let a equal to sine x. Well, you can think of this alternatively as, I don't know where to write this, but maybe 1 minus a squared divided by 1 minus sine of x. 1 plus sine x on this side. Okay, and when you have this, you can think of, hopefully I'm writing this correctly, you can think of, well, we know that 1 squared is just 1. This can be equivalent. Let's look for the solutions. Hold on a second. Equivalent, so what they have done here is factoring the numerator. So they're saying that this is equivalent to 1 minus a times 1 plus a in the numerator. I guess I shouldn't have written any of these because I didn't convert those to a. But yeah, so this is the numerator. So, oops. So let's apply that with the sine squared now. So forgetting about our a. I just wanted to simplify it by writing it like that. So instead we'll have 1 minus sine of x times 1 plus sine of x divided by 1 minus sine x is equal to 1 plus sine x on the other side. And as we can see here, we have the same thing in the denominator as we do in the numerator, right? Because they're being multiplied, the two brackets in the numerator, you can cancel them out, and we are just left with 1 plus sine x is equal to 1 plus sine x on the right-hand side. So we see that left side now equals right side, and that is our QED. That is our proof solved. They asked for proof, and we've solved it, so QED. Let's look at the solution. And we are using the same identities for secant x and tan x. And after substituting those in, we will have to find the common denominator for this fraction here, which we did this step to this step. And then instead of being divided by this fraction, we are now multiplying by the reciprocal of this fraction in the denominator. And then we use the Pythagorean identity to replace the numerator. Okay, and expand it and cancel out to give the proof. Okay, correct solution. And that's all for that question. We have just one more. So our question number 7 asks us, what are graph quadrants? So let's draw out a graph. So if we're given, well, we know, I guess I should say instead, that a graph consists of y on this vertical axis here, and x on the horizontal axis, right? So we know that the top of this vertical axis is the positive y and the bottom is the negative y. And we also know that the right side of the horizontal axis is plus x and the left-hand side of that is minus x. So that leaves 4 quadrants. We have 1 quadrant, 2 quadrants, 3 quadrants, 4 quadrants, right? And quadrant just essentially means the, well, quad is 4, so when we split the graph into 4 parts, we have 4 quadrants. So here we have quadrant 1, here we have quadrant 2, here we have quadrant 3, and here we have quadrant 4. These are in Roman numerals, so just know that. And that's how they're usually labeled. And as you notice, I counted them in a counterclockwise way, okay? So from these quadrants, you know that everything within this quadrant here has a positive x value and a positive y value because of where it's located. It's only on the positive side of the x-axis, and it's only on the positive side of the y-axis. So positive x and positive y in the first quadrant. Now in the second quadrant, we have the positive y, but the negative x. We have negative x and positive y in this second quadrant. In our third quadrant, we have the negative x side of the axes, and we also have the negative y components. And finally, in our fourth quadrant, we have positive x and negative y. Okay, so let's look through the solution because there's also an example we can go through. So in the Cartesian plane, it's a 2-dimensional graph that contains all negative and positive values of x and y. So based on these values, we can divide the Cartesian plane into 4 different sections called quadrants, and they are bounded by the x and y axis, or axes. The first quadrant, let's see if that's showing. First quadrant is located in the upper right corner, and we have the, let me just circle them as we go. So we have our first quadrant, we have both positive x and y. Second quadrant here, we have negative x and positive y. We follow along here. The third quadrant is located in the lower left corner. we saw. And that's a section where both x and y are negative. And lastly, our fourth quadrant, we have the positive x and negative y. So we notice that we label these in a counterclockwise manner. So starting from our quadrant 1, where we have positive x and positive y. And then we also notice it says here that when quadrants are diagonal from each other, they are similar, as in we both have the same signs. So this one has two of the same signs here, this has two of the same signs, and then for these across from each other, we have one negative and one positive, one positive, one negative, same thing. Okay, so this one says here that we're going to try a sample problem. So if we need to graph the points 5, 4, so we have 5, 4, well, that's an x value, and that's y value, remember? So we have in the house, that's how I remember it. I always remember x is in the house and y is up the stairs. So that can help you with order. So positive 5 and plus 4. Now I don't have labels, obviously. You can see I don't have labels on my graph, but this would show the general manner I'm finding our 5, 4 point. Let's just do one other. So we also have here given minus 4 and 2. So let's try to find that. Well, minus 4 is our x value. So that means in the house, minus 4. And then we have upstairs, or maybe if that was a negative, down the stairs. But anyways, a 2. So going up 2 because it's positive 2. And we will get something like this. Sorry you can't see, but I'll show you what it looks like in a second. But that's how you would use the quadrants. So here we go. So I just did the 5, 4 points. We have negative 4 and 2. And then finding negative 1, 3, well, we go in the house negative 1 and down negative 3. These axes aren't labeled, but it's the same where this one is y and this horizontal one is x. And then we also have 5 and 3. So that's in 5 and down, 5 and 7, and down 7 since it's negative 7. All right, correct solution. And we are cutting close on time. That's all for today. And let's go back to this. So that's all we're going to be covering today. If you did find this helpful, please leave a like and subscribe so that you can be notified of when we do another Q&A. Also hit the notification bell. If you want to submit any of your own questions, you can see the links in the description below, like I said before, and try to submit them there. So thank you for watching.